Hello and welcome to the Electronegativity, Bond Polarity, and IMF's video activity. So we should begin with electronegativity. Electronegativity measures how strongly an atom attracts electrons when it forms a bond. And so the trend we see is that it tends to be high for the nonmetals, with fluorine being the highest element on the periodic table, and it is low for the metals and transition metals. So we tend to see low values towards the left side, and particularly as we go downwards on the periodic table. And so here we have a table of values of electronegativity. And so again, fluorine's the highest, listed right here in the upper right, and the elements at the lower left are the lowest. You'll notice the transition metals are left off this particular table, but other tables would have it. And so I want to point out that the noble gases are left off the list. You might be wondering about that. Well, it mentioned earlier that electronegativity talks about how elements behave when they bond. Because the noble gases don't really bond, we don't really have or need really good electronegativity values for them because they don't do a lot of bonding. And so I want to give you guys a handy mnemonic for remembering the top several elements in terms of electronegativity in descending order. And that mnemonic is phone, call, break. So FON, phone, there's our three highest. Chlorine is number 4, there's call. And then bromine followed by carbon, there's the break. So phone, call, break is a good way to remember those top several elements. So how do we use these electronegativity values? Well, it's very simple actually. We just do subtraction. So we find the difference in electronegativity between the two atoms forming the bond, and that's going to help us predict what type of bond will form. So for example, if we bond nitrogen to nitrogen, nitrogen has an electronegativity value of 3.0, so 3.0 minus 3.0 of course gives us 0 electronegativity difference, and that means that our atoms are sharing their electrons completely equally, and we refer to this again as a nonpolar covalent bond. And if we bond chlorine and bromine together, these two elements are very close in electronegativity with a difference of only 0.2. Although our electronegativity values aren't exactly the same, they're so darn close that we consider this also to be a nonpolar bond. And anywhere up to a difference of 0.4 is considered to be nonpolar. So again, if our electronegativity difference is anywhere from 0 up to 0.4, we consider that bond nonpolar, meaning the electrons are shared equally or nearly equally between those two elements. And moving on to polar bonds, if we have a difference of 0.5 up to 1.7, that means we're sharing electrons, but we're no longer sharing them equally. So for example, if we combine oxygen and sulfur, oxygen has a value of 3.5, sulfur a value of 2.5. The absolute value of our difference is 1.0, which means that we're well within this range. So this is a polar bond. We're still sharing electrons, it's polar covalent, but we're not sharing them equally. They're going to hang out more, spend more time at the higher electronegativity end of the bond. So in this bond, the electrons would spend more time near the oxygen and less time near the sulfur. Finally, we have ionic bonds. These occur when our electronegativity difference is quite large, typically 1.8 or more, but these values do vary a little bit from source to source, so I ask that you stick with the values I present in this video, and they're consistent with the values presented in the textbook. So again, when we have these large electronegativity differences, this tends to occur when we bond metals and nonmetals together, and this is where we form, again, ionic bonds. So our difference is so dramatic in terms of electronegativity that we're no longer sharing electrons, we're actually exchanging them. In other words, our chlorine is so much higher in electronegativity than the potassium, the chlorine's just going to rip electrons away from the potassium. There's no longer any sharing between them. And that's what this diagram right here shows. So a nonpolar covalent bond, our electrons are shared equally or nearly equally. When we get to a difference of 0.5 up to 1.7, that's where we have our range in which we're polar covalent. So we're sharing, but not sharing equally. The electrons spend more time at the higher electronegativity end of the bond. And then finally right here, if our difference is 1.8 or greater, then we have electron transfer and we form this type of ionic bond. So you can see there's not any sharing here. These look like they're overlapping each other. That's how we share the electrons, as we overlap the atoms. But these actually look like hard spheres next to each other, and that's meant to show that we're not sharing electrons between these. So I'd like you to pause the video and please complete questions 1 and 2 in the activity. Now that we've discussed bond polarity, let's move on to talk about intermolecular forces. So intermolecular forces, or IMFs for short, they exist between molecules. So they're different than covalent bonds. Inside of our HCl molecule, the H and the Cl are bonded together with a covalent bond. However, between the molecules of HCl, we have these much weaker attractions that we call intermolecular forces. Again, inter means between, so these are between molecules. So we have the covalent bonds inside, and then the intermolecular forces between. And so we're going to talk about three different types of intermolecular forces, and the first one we're going to mention is going to be dipole-dipole attractions. So any molecules that contain polar bonds, polar covalent bonds, and we just talked about how to determine if a bond's polar. These molecules containing polar covalent bonds are going to display these dipole-dipole attractions. Because we have this uneven sharing of electrons, one end of our molecule is more positive, one end more negative, and this can result in attractions, weak attractions to neighboring molecules. A variation of the dipole-dipole attraction is what's known as the hydrogen bond. I want to point out hydrogen bonds is a very confusing name. So this name stuck. Unfortunately, years and years ago, people decided to call these hydrogen bonds, but they're not true bonds. They're actually intermolecular forces. So they're weaker than bonds like covalent bonds and ionic bonds. But the name stuck, and now we're stuck with it. And countless introductory chemistry students have been confused by this name over the years. So don't let it trick you. Hydrogen bonds are not bonds. They're intermolecular forces. And so these exist between molecules that are extra super duper polar, essentially. So when we have very, very large electronegativity differences in our polar covalent bonds, this is where we tend to display hydrogen bonds. It's the same idea as dipole-dipole attractions. It's just this greater degree of polarity makes these charges a little bit bigger, and consequently our attractions a little bit stronger. So what do we need in order to have hydrogen bonding? Well, the very polar type of covalent bond we need is we need to have a hydrogen covalently bonded to a fluorine, an oxygen, or a nitrogen. So again, if you remember, those are our three highest elements in terms of electronegativity. Hydrogen's relatively low for a nonmetal in terms of electronegativity. So the result here are these very, very polar bonds resulting in this extra strong type of dipole-dipole attraction called hydrogen bonds. And just to be clear again, these dashed lines, these weaker attractions between molecules are our hydrogen bond. The covalent bonds are something else entirely. So this covalent bond is not a hydrogen bond. The hydrogen bond exists between molecules. I know it's really confusing. If you have questions, that'd be a great thing to post up in the discussion board. And our final type of intermolecular force is what's known as dispersion forces. And dispersion forces occur in their primary attractive force between nonpolar molecules. So if our molecule contains entirely nonpolar covalent bonds, this is the type of attraction we'll tend to see. And so a molecule that's nonpolar tends to be nonpolar if you average together the electron positions over time. But at any given moment, those electrons might just happen through random motion to be towards one side of a molecule. So what does this mean? Nonpolar molecules are nonpolar if you look at them over a wide span of time, but if you take like an instantaneous snapshot of them, at that given moment they might actually be polar. And the motion of the electrons in this atom or molecule can actually influence this neighboring atom or molecule, and they can both temporarily be polar and create these temporary attractions. And these are known under various terms. We know these as dispersion forces, but you might see them in other resources called London dispersion forces, London forces. Some people call them van der Waals, but we'll just call them dispersion forces. Just be aware you might see other names for them. All right. So here's our summary of our different types of IMFs. They list here covalent bonds and ionic bonds. These are much stronger and they're sort of separated from the between molecules or intermolecular forces. So our intermolecular forces are hydrogen bonds, which are the strongest IMF, but still much, much weaker than these other bonds. And then dipole-dipole attractions, which are sort of intermediate in strength. And then finally dispersion forces, which are these temporary and weak attractions due to fleeting and temporary polarities of these nonpolar molecules. So why do we care about the IMFs? Well, IMFs are actually really important. Although they're much weaker than bonds, they control the physical properties. So the bonds control the chemical properties, and the physical properties like boiling point, melting point, things like that are controlled by the IMFs. And so when compounds change state, when we boil or melt, when we freeze or sublimate, any of those types of processes, the IMFs change, but the bonds do not. And the trends we see are polar compounds, those with strong IMFs, tend to be soluble in water. They tend to have higher boiling points and melting points, and they tend to be harder, versus compounds with weaker IMFs tend to be not soluble in water. They tend to be nonpolar, and they also tend to have lower melting points and boiling points. So I'd like you to pause the video and complete questions 3 through 5. Just note, to figure out some of the items in question number 4, you will need to determine the structure of those molecules. You'll have to know which atoms are bonded to which to determine the correct intermolecular force. And once you finish that activity, then I suggest you roll on over to the discussion section of Canvas and post up your questions and comments for your classmates. Thanks, and bye.